Hi everyone, welcome back to the CEE122 recitation, and today we will go through the homework solution for homework 9, which is for the week 10 content. Okay, so before I jump into the questions, I just encourage you to go through the equation derivation in the textbook, because it's really good to know like how the equation come from. And in this recitation video, what I'm doing is to show you how to apply those equations to solve the homework problem. So it is your effort to understand how those equations come from. And for this specific topic, the equation that we will use are derived originally from the RTT equation. So I strongly encourage you to go through the textbook and see how the textbook simplify or derive the equation that we'll use in this recitation from the RTT equation. Okay, so let's begin. In the first homework problem 7.16, we need to determine the discharge in the pipe and the pressure at the point B. Neglect the head loads and assuming the alpha, which is the kinetic energy correction factor, equal to 1 at all locations. So our plan is to find the velocity at the nozzle here. So we try to find the velocity here by applying the energy equation, which you have learned in previous course. And then we want to find the discharge by using this equation, because we know the discharge will equal to the area times the velocity. And then we want to find the pressure applying the energy equations to for this point B here. So to begin with, let's define the datum first. So let's define our datum to be at the nozzle point. Okay, so let's just start our first step, which we will apply the energy equation to find the velocity at the nozzle. This is V node. Okay, this is our goal. So applying the energy equation, the energy equations look like this. Let's just say this is the surface S, and this is the outlets O. Okay, so we denote O. This is S, and the velocity also is S to G plus the height will equal to P at the nozzle, which is at the outlet, plus B naught plus C. Okay. So because the point defined in this diagram, it's at the surface. So this P is equal to atmosphere, so it's 0. And it's for the outlet part, it's also open to the atmosphere, so this term is also 0. And the velocity on this reservoir surface is also 0. So we only have the rest of the term, and we know that Z is, we already defined our datum here, so these points have the Z equal to 5, because 1.5 plus 3.5 is equal to 5. So 5 will equal to the velocity term plus Z naught, which is 0 in this case. So by applying that say g is equal to 9.81 meter per square second, then we can solve the v naught, that is equal to 9.9 meter per second. Okay, so we now know the velocity at this point. Then we can calculate the flow rate for our second step. Flow rate is equal to V times A, and in this case it's 9.9 times pi over 4 times the diameter of this nozzle, which is 20 centimeter, that is equal to 0.2 meter. Okay, 0.2 meter square. So this is equal to 0.2 meter. Okay, so yeah, so that's our first variable that we want to solve, is the discharge rate in the pipe. So this is the answer will equal to 0.311 cubic meter per second. Okay, so that's the first variable. And the second variable is the pressure at the point B. So we apply the equation, the energy equation again, and now we define this. We want to compare the point at this water surface and the point at B. Okay, so now we change to these two dots I show on the diagram here. So again, energy equation, and now our purpose is to find the pressure at the point B. Okay, so let me write down the equation again, and when you do the quiz, you should also write down the original equations and then step by step simplify it so I can understand how you solve the problem, not just give me the answer. Okay, and this is P2 plus V2 plus Z2. This is PB, BB, ZB. Okay, so again, at the surface, P will equal to 0, and the pressure at point B is the things we want to solve, and we don't have the velocity term. Okay, and what else? Okay, that is how much we can simplify. Then we plug in a number. So for ZS, we already know is equal to 5 meter. That is equal to PB divided by gamma plus the velocity at the B point. And let me write here. We already know discharge, so the discharge will equal to VB times the area at the cross-section area of at the B point. So the velocity at B will equal to Q divided by AB, and that is equal to 9.9 divided by 0.311 divided by pi over 4 times the diameter of the pipe, which is 40 centimeter, that is equal to 0.4 meter. So this is 0.4 square, and this gives us the velocity is equal to 2.48. Okay, so now we plug the number back to here. 2.48 squared divided by 2g. G is equal to 9.81 meter per square second. And the last term, ZB, is equal to 3.5. Okay, because we already defined our detent at the nozzle. So this is 3.5. So the only unknown variable is the pressure, so we can solve it. So the gamma is a constant for water, right? So the gamma is equal to 9810 N cubic meter. And after you plug all those numbers in and use your calculator, then you can solve that PB is equal to 11654 Pa, which is 11.65 kappa. Okay, so that's it. You apply this energy equation twice for different points combination, then you can solve the answer for this problem. So now let's go to the next problem. Okay, so in this problem 7.23, we have the gasoline having a specific gravity of 0.8. The specific gravity is equal to 0.8. It's flowing in the pipe shown at the rate of 5 cnfx. So Q is equal to 5 cfx. And we want to know what is the pressure at the section 2 when the pressure at the section 1 is equal to 18 psig. So we want to know what is the pressure at section 2. And we also know that the head load is equal to 9 feet between the two sections. Okay, and we assume that the alpha, the kinetic energy correction factor, is equal to 1 at all sections. So again, we need to apply the energy equation to solve this question. So energy equation, that is P1 plus alpha E1 to G plus C1 is equal to P2 divided by gamma plus alpha V2 to G plus Z2 plus H, the head loss. Okay, and because we know the alpha is equal to 1, so we can ignore this alpha factor here because it is 1. Okay, then we define the points that we want to apply to this energy equation. The point 1 is at the section 1, and point 2 is at the section 2. Okay, and now we can start to simplify the equation. Can we simplify any term here? If we define the detent at the section section 2 here, then Z2 will equal to 0. Okay, so I guess that is how much we can simplify here. Now we start to plug in the number. So for the pressure turn, we will need to do some unit conversion. 18 psig is 18 pound-force per inch square. Times the unit conversion 1. 144 inch square divided by feet square. So basically you convert the inch square to the feet square and divide by the gamma. And we know that the gamma for water is equal to 62.4 pound force per cubic feet, and we have the gasoline's specific gravity equal to 0.8. So the gamma for gasoline is 62.4 times 0.8. Okay. So we have the gamma for gasoline equal to 0.8 times 62.4 pound force divided by cubic feet. And we plot the velocity turn. So the velocity at section 1 is equal to the discharge divided by the area. The discharge is 5 CFAs, which already given by the problem. Then we divide the area, that is equal to 0.8. Okay, 0.8. This gives us 6.25 feet per second. Okay, so plus 6.25 divided by 2g, and g is 32.2 feet per square second, and plus z1. z1 is 12 feet. Okay, so 12 here, and this will equal to P2 is the variable we try to solve, and sum the specific gravity times 62.4 for the gamma value, plus the velocity, and again we can apply the same equation, that's Q divided by A2, and this is 5 divided by the A2 is equal to 0.2. This gives us 25 feet per second. Plug this number back. 25 divided by 2 times 32.2, and this needs to be squared as well as this term. Okay, and the last term is the head loss, and the head loss is already given, which is equal to 9 feet. 9. Now the only unknown variable is this P2, so you can solve this easily, and this will give you that P2 is equal to 2287 PSFG, and this will equal to 15.9 PSIG. Okay, so as long as you know how to define the points that you want to apply to the energy equation, and you know how to do the unit conversion, then this one should be straightforward to you as well. Okay, so let's move on to the next question. In problem 7.25, a reservoir with water is pressurized as shown. The pipe diameter is equal to 1 inch, The head loads in the system is given by this equation. Okay, let's write it down. Head loads is equal to 5v squared divided by 2g. The height between the water surface and the pipe is equal to 10 feet. So the height difference between these two is 10 feet. Okay, and the discharge is 0.1 cubic feet per second. That is what we need. And the problem asks us to what's the pressure in a tank be to achieve such a flow rate. Okay, and we also assume that the kinetic energy correction factor equal to 1. So I will just ignore these in the energy equation. Okay, so again, we need to apply the energy equation for this question as well. We define the point 1 to be here and point 2 to be the outlet. And the energy equation, which we already repeated a lot of time, is equal to this. And because the alpha term, the correction factor, is equal to 1, so I didn't write it down here. 1 equal to P2 and plus the head loss. Okay, so again, we need to simplify it. P1 is the variable we try to solve. V1 is around 0, so that just say we can ignore this term. And then Z1, if we define the data to be at the point 2, then we cannot ignore Z1. Okay, and P2 is already open to the atmosphere, so this term is 0. V2 of course is not 0. Z2, or we define Z2 to be our data, so this Z2 will be 0 as well. And the head load is given by the problem. So let's rewrite the simplified equation. It will look like this. Equal to and the head loads have the equation here, and this V will equal to V2 because we calculate the head loads in this pipe. So if we combine these head loads with the kinematic turn, which is the velocity turn here, then we can rewrite it to be 6 V2 squared divided by 2G. Okay, now we can start to plug in the number. C1, so let's write it down. Gamma is 64. No, gamma. This is water, right? Yeah. Let's see. So gamma will be 62.4 pound force divided by cubic feet. Okay, so 62.4 plus Z1 is already given, that is 10 feet, and that will equal to 6 times the velocity. And how we solve the velocity? Again, the same equation Q will equal to A times V. So V is Q divided by A, and Q is already given, that's 0.1 cubic feet per second, divided by the cross-section area, that's pi over 4, times the diameter, which is 1 inch, and 1 inch is 1 over 12 feet. So times 1 over 12 feet square. And you plug this term back to here, 0.1 divided by 4 pi 1 over 12 square divided by 2g, and g is 32.2 feet divided by square second. Okay, so now the P1 becomes your only variable that you don't know, so we can solve it easily, and this gives us the answer 1329 PSFG, that is 9.23 PSIG. Okay, so again, applying the energy equation, define the 2 points that you want to apply to those to the energy equation, simplify it, plug in a number, and you can solve the problem. Okay, move on to the next one. In the problem 7.31 for the siphon, the elevations at A, B, C, and D are 30. Okay, so let's write it down. The A is equal to 30, ZB is equal to 32, ZC is equal to 27 meter, and ZD is equal to 26 meter, respectively. And the head loads between the inlet and point B is 3/4 of the velocity head. Okay, so the head load is equal to 3/4 of velocity head. So let me write to the right part because it's inlet to the point B. So HL and inlet is equal to 3/4 of the velocity turn, and halos between the point B and the end of the pipe is 1/4 of the velocity head. So HL outlet is equal to 1/4 velocity head. Okay, and for this condition, what is the discharge and what is the pressure at the point B? So we want to solve the discharge and we want to solve the pressure at the point B. The pipe have the diameter equal to 25 centimeter, that is equal to 0.25 meter. And assume that the correction factor is equal to 1 at all locations. So again, we will ignore this factor in our energy equation. So that's first, because the velocity inside this pipe should be the same between the inlet to the point B and point B to the outlet, because we assume that the fluid is incompressible and the area is not changing. So we can say that the total head loads is the sum of these two head loads. So this gives us the total head loads will be V squared divided by 2G. Right. Okay. So our plan is to apply the energy equation from the point A to point C to solve the velocity and to find the flow rate, and then apply the energy equation again from point A to point B to solve the pressure at the point B. Okay, so that started. First, energy equation we apply to the A to C, and PA plus V A squared 2G plus ZA equal to PP see. PC VC squared plus ZC, and we need to plus the head loads as well. And the head loads is equal to this kinetic turn. So this also VC 2G, because the water will flow from here to here, so it will have the halos because it's past this pipe. Now do the simplification. Open to the surface, so this PA is equal to 0, PC is equal to 0, and it's at the tank, so we assume that there's no velocity turn at reservoir A. Okay. So now we can plug in the number. ZA is 30 meter, will equal to ZC is 27 meter plus 2 velocity term, that is 2V, that's use, not VC, let's use BP in a pipe. Times 2P square 2G, cancel these two, so these 3 equal to BP G, and G is 9.81 meter per square second, so VP is 5.42 meter per second. And to find the discharge, apply the equation. Q is equal to VP times AP. So at the pipe, okay? So P stands for pipe. And we know the velocity, and we know The diameter of the pipe is 0.25 square, and this gives us a discharge equal to 0.266 cubic meter per second. Okay, so this is our first item that we try to solve. The second one, we want to solve the pressure at B. So let's apply the energy equation again, but now is to A to B. So PA plus VA plus DA equal to PB plus VP, because in the pipe so it's 2 to G plus ZB, and plus the inlet, the halos. The halos for these parts, for the inlet part, is 3/4 VP square to G. Right. So again, these two terms can be cancelled, and we already explained why. And the pressure B is the things we try to solve, and we know the rest of the term, so we just plug in a number. ZA is equal to 30 meter, and ZB is equal to 32 meter. Okay, so this is 32, and you combine these two together. And you know the VP is equal to 5.42, and the G is equal to 9.81. So the PB, the pressure at the point B, is the only variable you don't know, right? Therefore, you can calculate the PB is 1 constant, that's gamma for the water, is 9810 Newton per cubic meter. Okay, so now this PB is the only variable you don't know the value. Okay, then you can just use your calculator and you can solve that PB is equal to minus 45.3 kappa. Okay, so applying the energy equation twice for different point combination, then you can solve this problem. Now let's move on to the next one. In the problem 7.40, a water discharge of the 8 cubic meter per second is flowed through this horizontal pipe, which is 1 meter in diameter. Okay, we have the diameter equal to 1 meter. If the halos is given us 7 times the kinetic turn, how much power will have to be supplied to the flow by the pump to produce this discharge? And also, again, we assume that the correction factor alpha is equal to 1 at all locations. So we know the halos in this pipe 7 times the kinetic turn. Right. So our plan is to find power using the power equation, and the steps are to find the velocity in the pipe using the flow rate equation, and then find the head of the pump using the energy equation, and then we can calculate the power. So So let's start with the flow rate equation. Step 1, flow rate, and again Q equal to A times V. So V is equal to Q divided by A, that is 8 divided by pi over 4 times the diameter 1 square. This gives us 10.2 meter per second. Then the second step, we apply the energy equation. We apply the energy equation to the surface of this reservoir. So this is 0.1, and then the location 2 is at the outlet of this pipeline. So this is 0.2. So 1, 2, and we can start to write the equation down, plus the alpha and because we have pump here, so we add this pump head on the left hand side. P2 comma plus alpha P2 divided by 2G plus C2 plus H turbine plus H head loss. Okay, and here start to simplify the equation. The alpha is always in this question is equal to 1, and we don't have the turbine here. And the surface is open to the atmosphere, so this one P1 is equal to 0, and that's define the datum to be at the level. That's fine because it already gives us the elevation here, so let's just use that for our calculation. We don't want to define another datum in this case. And the pump is the things that we try to solve, and we already know and we don't have the velocity term for the surface, right? And point 2 is also open to this atmosphere, so P2 is equal to 0. We know the velocity V2, which is equal to 10.2. Z2 is also known, and the head loss is equal to 7 V2.2 G, because here is the head loss. Cool. Then now you basically can see this equation that this HP is the things that we don't know. But let's write the simplified equation down here so you can see it more clear. And I add these two terms together. Okay, so this 8 V2 plus D2. Okay, so Z1 is 40 plus HP equal to 8 V2, that is 10.2 squared divided by 2G. G is 9.81 meter per second squared, plus Z2. Z2 is 20. Because 20 here, 40 here. Okay, so we can solve that HP is 22.4 meter. Then we can apply the power equation for the third step. That's the power equation. The P of the power is Q times gamma times the pump head. And the Q is already known, is 8 cubic meter per second times the gamma. This is 9810 Newton per cubic meter for water, and times the pump head that we just solved is 22.4. This gives us the power equal to 1.76 million watts. Done. Okay. So we follow our plan to solve every variable step by step. First, we solve the flow rate, then we apply the energy equation for the point 1 and point 2 to figure out the pump head. And then we apply the power equations to turn this power pump head into the power. Okay, so let's go to the next problem, 7.47. A small-scale hydraulic power station is shown. The elevation difference between the reservoir water surface and the pump water surface downstream of the reservoir, H, is equal to 24 meters. The velocity of the water exhausting into the pump is 7 meters per second, and the discharge through the system is 4 cubic meters per second. The halos due to the friction in the penstock is negligible. Find the power produced by the turbine in kilowatts. Okay, so we want to find the power of the turbine. Okay, so how can we solve this? So our plan will be applying the energy equation from the upstream water surface to the downstream water surface, and then we can apply the power equation. So let's put that into action. First, we want to apply the energy equation between the upstream surface, this is point 1, and the downstream surface, this is point 2. And let's write down the equation. P1 plus V1, 2G plus C1 equal to P2 plus V2 plus C2 plus H load and plus the turbine head. Okay, and simplify the equation. P1 equal to 0 because it's at the surface. P2 is also equal to 0 because it's also at the surface, and they don't have the velocity term. And we define the dead end to be at the point 2. So Z2 is equal to 0 and Z1 is equal to 24 meter in this case, because H is equal to 24 meter. The halos, and we have, so the halos is already also given. No, the halos is negligible. So we actually don't have the halos here. And we do have the velocity term because the water flush out this way. So we cannot ignore this part. Okay, so the simplified equation will be Z1 will equal to V2 divided by 2G plus the turbine head. And we already know this is 24. V2 is the variable we try to solve. Actually, no, we already know the V2, so let's plug in the value. V2 is 7 meter per second, so this is 7 squared divided by 2G. G is equal to 9.81 and plus the turbine head. Now we can solve the turbine head, that is equal to 21.5 meter. Okay, so we halfway to there. Now we just need to apply the power equation to turn this turbine head into power. So P is equal to Q gamma HT. So Q is also given is 4. Gamma for water is 9810 Newton per cubic meter. Then the last term is the turbine head, that is 21.5 meter, and this gives you the power equal to 844 kilowatts. Okay, so I think you can figure out the pattern of all these problems. You apply the energy equation and try to solve the turbine head or pump head and use the power equation to turn that head into the power. So this is the end of this recitation, and I will see you in the in-person recitation for the quiz. Bye.